So here I am trying to solve the problem of too many inputs to the network. And why do I have too many inputs? At every possible location of the sliding window, I am taking the crop, resizing and feeding this as input to the network. So how will I solve this problem? Note that internally when you are doing the convolution operations, you are anyway using the sliding window technique. So maybe by using the convolution layers, I should be able to solve the problem of location. And now I am only left with the problem of scale, for which I am using the image pyramid. And typically it's common to use images of 6 different scales to do the processing. So if I can somehow give the entire image as input to the network, these 6 images as input, then I'll be able to drastically reduce the number of inputs to the localization framework. But can I do that? Can I just feed the entire image as input to the network? I'm afraid not. Why? We already discussed this. The CNNs usually expect the image input to be of fixed size. For example, if it is AlexNet or VGGNet, it will expect an image input of size 224 by 224. I can't just take the different scales of these images and give this as input to the localization framework. This may not work. But if I can somehow get rid of this constraint, then it will be the best case scenario. So first, let's try to understand why this constraint is there in the first place. Let me explain this using a simple example. I'll take a 6x6 image and I'll do the convolution using padding of 1. That is, these zeros that you are seeing is for padding, and I'll use a stride of 1. In my first layer, I'm using a filter of size 3 by 3. And what happens now, I'll get a feature map that is of size again 6 by 6. Once I do the pooling, I'll get a pooled feature map output that is of size 3 by 3. And I'll stretch this to a one-dimensional vector of size 9 by 1. Okay, so far so good. I don't have any problem processing this image. What if I take a slightly bigger image, that is 8 by 8 image? Remember, I have to use the same parameters here. I have to use the pooling of 1, stride of 1, 3 by 3 filter and 2 by 2 pooling. That is, I should not change the network at all, but still I should be able to process a image of a bigger size. So in this case, what happens? If I am convolving this image with the 3 by 3 filter, I'll get back 8 by 8 feature map output. And if I do the 2 by 2 pooling, I'll get a feature map output of size 4 by 4. If I stretch that to a one-dimensional vector, my feature vector will be of size 16 by 1. So even for a big size image with the same convolution neural network and same parameters, I'm able to do the processing in the convolution and pooling layers. In the convolution and pooling layers, so far I have no problem in processing images of different sizes. So what is the problem? Why do we have the restriction? The restriction or constraint is coming from the fully connected layers. Here, how do we do the fully connected layer computations? I'll take this feature vector, do the dot product with this array to get this output, and the same feature vector I'll take the dot product with this vector to give this output. So basically I have one output per class. But what happens if the image size is slightly bigger? I am having a 16 by 1 feature vector. Can I take a dot product now with this array? I can't, because the golden rule of a dot product is that the sizes of these two arrays should be same. So that is the reason why I can't use images of different sizes. The constraint is coming from the fully connected layer. Because in the fully connected layer I am using the dot product operations, I can't take the dot product of these vectors. So this is where the constraint is coming from. Now the question is, can I solve this problem? Can I solve the problem of constraint at the fully connected layer? If so, how? One idea is, we have already discussed this, that I can implement the fully connected layer as a convolution operation. That is, instead of using a 9 by 1 filter, I'll just use a 3 by 3 filter. I'll just rearrange this vector in terms of a matrix. Okay. Now again, even in my convolution layer output, instead of using the feature vectors, that is, instead of converting this feature map to a one-dimensional feature vector, I'll directly use the feature map. Let's see what happens in this case. For the first filter, I convolve this output feature map with this filter to give this output. Next, what I have to do is I have to convolve these two matrices to give this output. So for this image, I don't have any problem. I got back the same outputs. But what happens if the image is slightly bigger? In this case, when I convolve these two matrices, I'll get an output of size 2 by 2. And then when I convolve these two matrices, I'll get an output again of size 2 by 2. So now the question is, for each class, I'm getting a 2 by 2 output. I'm actually expecting one single output for every class. But for each class here, I'm getting a 2 by 2 output. The question is, does this make any sense? If so, what does this mean? Let's try to understand this in the next video.